Okay. All right, here we go. Oh, it's a little oddly projected there, but all right. So I'm Matt Siegler. I'm part of the Diviner team, and I'm talking about some really interesting results we might have near the poles of the moon. Um, the first time we talked about this was roughly about 2 years ago, and then none of us have really worked on it since. So as part of my postdoc at JPL now, I've sort of taken up some of this project. So let's see what we can learn from these cold places on the moon. And this is just an example of this really cold crater here. So this is Hayworth Crater near the South Pole. So the South Pole is sort of down here. And within Hayworth Crater, there are doubly shadowed craters or triply shadowed craters even that get really, really cold. We'll talk about how cold. All right, so briefly, I'm going to just give you an overview of what lunar temperature models would look like, just so you can get a feel of it. Then we'll talk about some of the new data and what we might be able to say from it, and what does this data actually tell us about anything, and then sort of how we're progressing along this project and what tools we're using. Okay, so just brief overview. Here's temperatures at the equator of the moon, right? You have noon, you go into midnight, and next day again. So that's what it would look like over a whole year, right? Here's 12 cycles. Here's what it would look like at different latitudes. So if you get to high enough latitudes, you eventually get polar night, right? Where you have basically 6 months of darkness. So you have this long night. So those are some of the extremes in the temperatures. So I'm going to show you a bunch of plots that look sort of like that polar night one. So just so you get a feel of what it would look like. But anyway, so here's what you might expect for a flat surface at 89 degrees, is something with temperatures like this. So sort of before the mission, that's what we planned for, is okay, maybe there'd be a few craters that would be a little colder. Here's just an example of, let's do something crazy. Let's take the moon and put it at 20 AU, all right, and have it be really cold out there. Cut down the sunlight by that much. You could get something that would be really cold. That's sort of the minimum floor that Diviner was designed to measure originally. Something getting down to maybe 30K or something. And what you could do then is, if you really did get something that cold, different things will affect the temperatures in different way. You might change the thermal properties of that place, and you'll get quite different cooling curves over that long winter night. And so that could tell you something about the thermal properties, and that's originally what I was hoping to do with my thesis, was see very different thermal properties here at night and map everywhere that there was ice, because ice would be high thermal inertia. But it turns out we don't see anything like that. Then you might look at a new project here is, could you actually get some information out about geothermal heat flow of the moon? So, if you had an area that was that cold, the heat flux from underneath actually will have a substantial change on the surface temperature. So trying to look at modeling that sort of thing. So too bad no place gets that cold on the moon, right? Well, now we can look at the actual temperatures. And so this is a plot of the modeled temperatures from Diviner. This is the yearly minimum temperatures. Just to pick out some interesting places we might look, I said, okay, let's cut off temperatures at 30K here. This is places. So this is now that Hayworth crater again. And so here's this cold crater within Hayworth that I was talking about looking at. You can even say, okay, let's find places that the model, all right, this is not the data yet. The model is telling you that it dips below 20 Kelvin or 25 Kelvin. And so let's look at the data from that place. Here's what the data at winter solstice of the second year of the mission looked like. As you can see, all right, we are seeing especially cold data in that cold location. All right, here's just a pretty way of plotting it. All right, and so here we see, this is something that David Page showed in his plenary talk the other day. But we can see that we actually get something that looks like reasonable temperature curves. All right, this is 3 years of data, so we see the summer and winter, summer, winter. All right, and what I've done here is the error bars are proportional to how many data points you have in your bin. These are 1-day time bins here. So, damn, that's cold. All right, we're seeing places. So I'm just going to throw out some of the bigger error bar stuff because that was where we had less statistics. And we can see places that if we really take it at face value, we're getting temperatures down in this second winter here, where I was showing the map for, down to as low as 18.5 Kelvin or so. Okay, So if we're really going to believe those temperatures, this is the coldest place we've ever measured on the moon, and if I'm not wrong, anywhere. So anywhere in the solar system. So that's pretty good. I mean, this is colder than the surface of Pluto will be. And then here we could see, and just in case you think that this is some data anomaly, there was something wrong with those particular data, which we still need to work on, and that's why we're sort of saying it's all preliminary stuff. We do get other points the year before and after that are pretty much just as cold. So we have some constraint on these very low temperatures, and they seem repeatable. This actually beats our previous record in the North Pole. We talked about Hayworth Crater, where it got down to about 20.5 Kelvin, or a little less even. And frankly, the insolation pattern of this new cold spot is a lot easier to work with as far as understanding the data. Just to talk about what these data might mean in the global context. So if you just take the low temperature at face value and this heat coming out, and you assume that you really have no incident light hitting that area at that time, that it's so cold that you're in complete darkness, geothermal heat from below should actually warm the surface. And you could just take, if you had, this is a unit emissivity, which you might not have, especially in these cold places, all right? We don't really know what controls emissivity in these cold places. You can just take that temperature that you measure and convert it into a local geothermal heat flux from below. And we can see that these new places here are actually constraining values quite a bit lower than what the Apollo heat flow measurements measured near the equator. Does this make sense at all? Well, actually, yeah. So here is this big thorium anomaly we call the Prochilerium creep terrain. And the Apollo 15 and Apollo 17 data sets have been known, or the landing sites have been known to be near very thorium-rich and uranium and potassium all concentrate in this area. Near this area, and a bunch of people have written things about this, that they think, okay, Apollo 15 and Apollo 17 measurements were probably biased in their heat flux by these crustal anomalies. We don't have those sort of crustal anomalies near the poles, so that makes these places really interesting as possible views into, what's the general crustal composition and what's the heat flux from the mantle below. So that's the sort of things we're trying to get out of it. You can look at another way. Here's just taking the thorium anomalies and seeing that it does follow a consistent trend of less thorium from orbital data, lower heat flow constraints. So everything seems to be pretty consistent. And this is one of the projects I'm working with my postdoc advisor, Sush Makar, looking at modeling this global heat flux, actually taking these thorium distributions, trying to convert them into local heat anomalies and doing whole big global thermal models to see if we can repeat the data we get. So this comes now to another issue with these weird cold places, is they're really hard to match with our data. So something, and this is one of the reasons we've been so slow on this whole process, is trying to figure out what's actually being measured. Because if we just run our general straight thermal model, so this was for Hermite in the north, we see that the data seems to be implying a much higher yearly amplitude in temperatures. So that implies it's either a much lower thermal inertia or very different albedo. There's lots of different things, but thermal inertia is the main thing that could cause you to have such a higher amplitude. Again, we have that same problem with the new data here from, this is from Hayworth Crater. And you see we just get much higher temperatures in the winter and summer than the general model would create. We don't see this sort of discrepancy with our model at warmer temperatures. All right, you see here Shackleton Crater, for instance. Everything seems pretty well. When you start to get colder, this is Dergolaki Crater, you start to see a little more variation. We can look at something that has a bunch of temperatures. So here's we can look at Amundsen Crater as a good laboratory. So we could see that across this transect here, we get a big drop in temperatures. And we could basically see that yeah, if we take our general thermal inertia model, which works very well at the equator, matches pretty well, but when you start to get these colder places, you start to diverge. This is actually something that maybe we should have expected beforehand. This is laboratory data from meteorite samples, where you actually see this plunging in thermal conductivity, which would plunge the thermal inertia at low temperatures below 100 K. And so it seems that maybe we can actually be measuring this new property in lunar soils, and it's not just something in these meteorite samples. And this is actually a surprise to come on meteorite samples. All measurements before this paper, which is, I think it first came out in 2010 data, actually for crystalline things, which people usually measure at low temperatures, you actually get a high spike in thermal conductivity as you get colder. And then as you get really cold, basically phonons, the jiggling of atoms, stop jiggling, and that's what you get this big drop. And so with amorphous samples like meteorites or soils on the moon or regolith on any body, you seem to just get maybe this drop off. So that might be really interesting for thermal measurements of any bodies, especially asteroids and everything. The same process should happen. So here we're just going to show a brief model of this. Looks like I missed a slide there. But anyway, we're not quite there yet at getting the model to match, but we're basically going forward with different models like this and giving it a try until we can get the best fit thermal inertia as a function of temperature. Just to show again that we're on the right track, the simplest thing you could do is just take your insolation coming in and say that you're in radiative equilibrium. That's assuming that you have no albedo and no thermal inertia at all. And we could see that our data seem to be falling on the yearly sort of trends. Oh, I see. These slides got switched. Anyway, that we would expect in both the Hermite crater and the Hayworth crater. Yeah, so I'm going to end with this. This is just to look at another process going on here. This was proposed actually as a measurement of orbital heat flow back in the 60s. And the conjecture why we shouldn't ever try to do this measurement was we would get horizontal heat flow from the warm rim of a neighboring crater. And so just to show you that we're also looking at that aspect of this, we're also trying to do three-dimensional models of neighboring warm places and looking for horizontal heat, which might actually be flowing into these cold areas as well. Okay, well, thank you very much.
We have time for questions. In a really cold place like that, it's just my wild guess. Maybe the radiation from the Earth may have an effect. No.
So in our full model, we do include the Earth as a radiation source.
Okay.
Yeah. So,
okay.
But I think this particular place is in Earth's shadow as well.
Oh, okay.
But yeah, that's a good point.
We have a question
Is there any indication that frosts have the same temperature-dependent thermal conductivity at low temperatures?
If rocks would?
Yeah, I mean, if frosts have the same,
frost.
like water, ice.
Okay. Possibly, but as far as in the lab measurements and stuff. Yeah. I mean, there are measurements of water ice. I think that someone has done at those temperatures, but honestly, I don't really think that measurements have been done. So I think there's a lot of room for doing measurements of of properties that we might expect to find on these planets at these low temperatures, because they might be acting very different than we expect.
Interesting.
we have time for another question, if we want.